Start?
Wait, 1 second. Hello, everyone. Welcome to this session of Students Learning Seminar. Today's talk is by Shrivathsa Pandelu from MMath first year. The title of the talk is Baire Category Theorem and some applications to functional analysis. Shrivathsa, please start.
Hello, everyone. I hope all of you are safe. Like I said, I'm doing my second semester at MMath here at ISI Kolkata. And today I'll be giving a talk on Baire Category Theorem. So first I'll be defining what a Baire space is, and then I will prove two theorems that give sufficient conditions of when a space is a Baire space. Then I'll use the Baire Category Theorems. Okay, so those theorems are called Baire Category Theorems. I'll use those theorems to prove certain theorems in functional analysis. I'll be assuming some background in topology and functional analysis. Now, this Baire Category Theorem is quite a fundamental result in this area of maths, and as I should say, it's quite useful also, especially in functional analysis. So now we define a Baire space. So suppose we have a topological space X. A subset A is said to have empty interior if it doesn't contain any open set. Equivalently, its complement has to be dense, meaning it should intersect every open set. And this equivalence is somewhat easy. If you have any set A, and if it has empty interior, that means it doesn't contain any open set, which means that every open set will intersect the complement, which means that the complement is dense. So we have this equivalence between a set being having empty interior and its complement being dense. Now the condition for a space to be a Baire space is that if you take a countable collection of closed sets with empty interior, then their union also has empty interior. Now the union obviously need not be closed, but we demand that the union have empty interior. So using this equivalent condition, it also means that if you have a countable collection of open dense sets, then their intersection should also be dense. Again, the intersection need not be open, but we demand that it be dense. So before giving an example of a Baire space, I'll give an example of something which is not a Baire space. So consider the rationals with the usual standard Euclidean topology. So the set of rationals is a countable set. So we can write Q as a union of singletons, which is a countable union. And in the standard topology, the singletons are closed sets. They're closed sets and they have empty interior. So we have Q as a countable union of closed sets with empty interior, but Q itself doesn't have empty interior because it's the whole space. So Q is not a Baire space. But on the other hand, we have, if you take any set with the discrete topology, then singletons are open. So any non-empty set has non-empty interior because they contain singletons. So there is no closed set with empty interior. So vacuously, anything with the discrete topology is a Baire space. And we'll give further examples, and we shall see that most ordinary spaces are going to be Baire spaces. So originally, this Baire used the word category. So he said that a subset A of a space X was in the first category if you cannot contain it in a countable union of closed sets with empty interior. And it was in the second category otherwise, it was in the first category, it was contained in a countable union of closed sets with empty interior, and second category if it wasn't contained. So in this terminology, a space is a Baire space if every open set is in the second category. Now the sets in the first category, meaning they are contained in a countable union of closed sets with empty interior, they are also called meager sets. So this terminology is somewhat the same spirit as what are called as null sets in measure theory. So null sets are those that don't really have any mass. So here, sets with empty interior, they don't contain any open set. So you could also think of them as boundaries of open sets or something. So they're negligible sets. They don't contain singleton null sets. And this notion of being a Baire space is in somewhat similar spirit as how in measure theory we require that null sets, the countable union of null sets is also a null set. Where this comparison is not a strict comparison, because in measure theory we had sort of forced this condition by requiring countable subadditivity of measures. But here, it's not always obvious when a space is a Baire space or not. But the point is that the requirement is that the countable union of null sets or negligible sets is a negligible set. Okay. So now what we have this small lemma over here. So it says that an open subset of a Baire space is again Baire. So in this sense, the condition of being a Baire space is hereditary towards the open sets. I'll just give a sketch of this proof. So we have take an open subset Y of a Baire space X. And if there is a closed subset A in Y, then with empty interior, we can show that the closure in X has empty interior in X. And the proof will, for the proof, if you have an open set contained in A closure, then the intersection with Y, you can argue that it's going to be contained in A, and it will sort of make A to not have empty interior. Anyway, so given this, if we have a countable collection of closed sets with empty interior in Y, then we look at the closures in X. That forms a countable collection of closed sets. And because X is Baire, their union has empty interior. Now coming back to Y, if U is an open subset of Y contained in union of A, then U is open in X because we assume Y to be open in X. So now U will be contained in union of A, which is contained in union of A in closure. And because union A in closure has empty interior, it forces U to be empty. So it follows that Y is also a Baire space. Now, so these are the Baire category theorems. Like I said, they give sufficient conditions for a space to be Baire. So there are two versions of the theorem, and I'll prove both of them, but the proofs are quite similar. So the first one says that a complete pseudometric space is a Baire space, and the second one says that a locally compact Hausdorff space is a Baire space. So I will define what a pseudometric is soon, but just keep in mind that if you're not comfortable with the pseudometric space, you can think of metric spaces as well. So now a complete pseudometric space and locally compact Hausdorff space. So these two categories of spaces are something that analysts and topologists you deal with most of the time. So for example, manifolds are locally compact Hausdorff spaces, and function spaces are complete metric spaces. Banach spaces are complete metric spaces, and so on. So a large class of spaces that mathematicians usually deal with fall under these two categories, which means that they are going to be Baire spaces. And once they are Baire spaces, we can prove a lot of other theorems as well. So what is a pseudometric space? So on any set, the whole point of a metric or a pseudometric is to define a notion of a distance. And this notion of this, we would like this notion of distance to satisfy some reasonable things which we think are nice. So one thing that we want is the metric the notion of distance should be non-zero, non-negative. So that condition is put on both the pseudometric and the metric. We also want symmetricness. So we want the distance from A to B to be the same as the distance from B to A, and that condition is demanded of pseudometric and the metric space. And we also want this triangle inequality. The difference between a pseudometric and a metric comes with this when the distance is zero. That's where the difference comes. So in a metric, when we deal with the metric space, we demand that the distance between 2 points is zero only if the 2 points are the same point. But in a pseudometric, we can have d of xy to be zero when x is not y. So unlike a metric space, we don't have a Hausdorffness or a T0 condition on pseudometric space. But we can still, because we have this somewhat at distance, we can still talk about the topology generated by a pseudometric space. So it's generated again, the topology is generated by open balls around points. And once we have a topology, we can talk of other things as well. And because we have this notion of distance, we can talk about sequences being Cauchy or convergent. But because 2 distinct points can have zero distance between them, the limits of sequences need not be unique. So in a metric space or in any other space, the limit, when there's a Hausdorff condition, the limit can be unique. The limit is going to be unique. But here we don't have it. So we can have sequences that converge, that that are Cauchy and have multiple limit points. And we can again talk about a pseudometric being a complete pseudometric space, where we say that every Cauchy sequence should have a limit point. And one more thing is that if 2 points x and y have non-zero distance between them, then we can separate them by open intervals. That's the same way as in metric spaces. If r is the distance between them, we can take r by 3 balls around each of them, and those open balls will be disjoint and separating these 2 points. So we have that much freedom. That's quite similar to metric spaces. Now, here is a pseudometric space which is not a metric space. So consider the space of all square integrable functions on 0, 1. So these are all functions such that the integral of the square is finite. Now we can define a norm. So it's not exactly a norm. Okay, so I missed a square root there. Anyways, we can define this norm as the square root of integral f square dt. And so it's not a norm, sorry, but it satisfies positivity and it scales properly, and we still have the triangle inequality. I missed the square there. So, now, using this norm, we can define a pseudometric as d of fg to be the square root again of f minus g square, integral of f minus g square. And here, the positivity and symmetric conditions are obvious, and so is triangle inequality. But we don't know d of f and f is 0, but we can have d of f comma g to be 0 when f is not equal to g. This happens whenever f and g agree almost everywhere. So, for example, if you modify f on a point, you can change the value of f at a point, and the integral is still the same. So, but the two functions are different. So this is a pseudometric space. But what we do is, so C is a vector space over here. We can look at the subspace of functions which vanish almost everywhere. And that's a proper subspace. And once we quotient it, we get something which is called L2 of 0, 1. And this metric and norm will descend to that space. And we get a metric space. And it's going to be a complete metric space as well. So that's one way to go from a pseudometric space to a metric space. We look at all, we go modulo and equivalence relation where the relation is x is related to y if the distance is 0. So we can go from pseudometric spaces to metric spaces. That's a different topic. So yeah. Now I'll prove the first Baire category theorem. So the idea is that, so what do we want to show? We want to say if we have a countable collection of closed sets with empty interior, we want to show that the union also has empty interior. Now to show if the union has empty interior, I need to show that it doesn't contain any open set. So what I'll do is I'll take an open set outside. I'll just take an open set, and I need to find a point outside the union of A. So the proof proceeds as follows. We try to find a sequence in X which is Cauchy, and we look at its limit, and we hope that the limit will not lie in the union of A. So we start. So let's say U is an open set, and we are given this countable collection A. Now A1 has empty interior, and U is an open set. So we can find a point x1 in U which is not contained in A1. And because U is open, we can find an epsilon 1 ball around x1 contained in U minus A1. Now take U1, we shrink the radius and take U1 to be the epsilon 1 by 4 ball around x1. We shrink the radius so that when we take the closure, it will still be disjoint from A1. Now, I want the closure to be disjoint from A1 because my sequence is going to lie in U1, and its limit will also be in U1, and I don't want this limit point to be in A1. So I want the closure to be disjoint from A1. Okay. So I start with U, I find x1, and I find epsilon 1. I shrink the radius, and so one more thing. So I take U1 to be the epsilon 1 by 4 ball around x1. So now, as I said before, if 2 points have non-zero distance, then we can separate them by balls. So the closure of U1 is going to be the closed ball around x1 of radius 1, epsilon 1 by 4. Anyway, so now I have U1. Now A2 is another set with empty interior, and U1 is an open set. So I can find an x2 in U1 minus A2 and repeat this process. So here's the picture. I have A1 and I have U. I pick x1 and I take u1. Then starting with u1, I choose x2 and I choose a u2 around x2 whose closure is distant from a2. And note that so I have epsilon 2 ball around x2. Right? So I'm shrinking the radius again to 1/4 the size. And now this time x2 is not in a1 union a2 because u1 is already distant from a1 and u2 is again distant from a2. And epsilon 2 is less than epsilon 1/2. Okay, and u2 closure is away from a is in u1 minus a2. And I repeat this process again. So having obtained un minus 1, I choose xn in un minus 1 minus an and an epsilon n greater than 0 such that xn, the epsilon n ball around xn is in un minus 1 minus a. And I shrink the radius again so that xn is outside the a1 union dots and then an, and epsilon n is less than epsilon 1/2 power n minus 1. And un closure is contained in, so un closure is in un minus 1 and away from each of the a1 through a. Now, since I keep shrinking the radius, the diameter of un is going to be less than epsilon 1/2 power n. And un closure will contain the tail sequence from xn onwards. So this means that the sequence xn is a Cauchy sequence. So it has a limit point. I pick one limit point arbitrarily. Because we are dealing with a complete pseudometric space, we know that limit points exist, but we also know that the limit point need not be unique. So I just pick an x, which is a limit point arbitrarily. And I know that because the tail sequence from xn onwards is in un closure, this x is also in un closure, which is away from an. So I know that x is away from an, x is not in an. So now I have found an x such that which is contained in u and it's not in any of the an's. And this means that un is not contained in the union an. So x is there and u was arbitrary and the collection an was arbitrary. So we have proved that x is a Baire space. Now the second Baire category theorem is quite similar to the first one, but instead of, so in the first one we use the completeness of the matrices. Here we use the compactness, specifically the finite intersection property. So again, we have been needing this small result over here. So if X is a locally compact Hausdorff space, then given a closed set A and a point not in A, I can find an open neighborhood U such that U closure is compact and away from A. So I can prove it in the end if someone is interested. But for now, let us skip it. So now again, we consider a countable collection of A and closed sets with an empty integral and a set open set U. Again, we this in the previous thing we found elements x1, x2, and so on. This time we find compact sets U1 and U2. Okay? So U is open and A1 has empty integral. So we find x1 in U minus A1, and using that result I stated, we find the U1 such that U1 closure is distant from A1, and the closure is contained in U, and the closure is compact. Now we repeat this process. So A2 has empty interior, and U1 is an open set, and so on. So having obtained UN minus 1 closure, we find a point xn in UN minus 1 minus an, because an has empty interior and UN minus 1 is open. And we find this UN such that UN closure is disjoint from an and contained in UN minus 1. In this way, we iteratively get this descending chain of compact sets. So UN closure containing U2 closure containing so on. And because UN closure is compact, we know that the intersection of these UN closures is going to be non-empty. So I take any element in that, and that is not going to be in the union of A. So again, this shows that U is not contained in the union of A, so X is a Baire space. Okay. So now we come to this open mapping theorem. Okay, so this is going to take some time. So anyway, how do we use this Baire category theorem to prove theorem? So what we do is we start with the space which we know has a non-empty interior. So it could be either a Baire space or an open subset of it because of that lemma. And then we write this space as a countable union of closed sets. And because we know the space is a Baire space and has a non-empty interior, we know that one of these closed sets should have non-empty integral. That's how we are going to use the Baire condition. So the open mapping theorem says that if we have x and y two Banach spaces and a continuous surjective linear map between them, then that linear map is also going to be open. Now, here I am going to be dealing with the somewhat strong hypothesis that x and y are Banach spaces, but we can weaken the hypothesis, and the proof is found in Grudin's functional analysis. So the stronger version of the theorem says that you can take x to be an F space, y to be a topological vector space, and instead of A being continuous, surjective, and linear, we can take it to be continuous linear, and the hypothesis requires that A of x is in the second category. To remind you, anything in the first category is something that can be contained in a countable union of closed sets with an integral. In the second category, not. So what is an F space? So we have this class of vector spaces. So a topological vector space is a vector space with a topology on it such that the operations, the addition and scaling from scaling of a vector, those two operations are continuous. An F space is a vector space over ROC with a metric on it such that again the operations should be continuous, and this metric should be translation numeric, meaning the distance between x and y should be the same as after translating by some a. And we also require this metric to be a complete metric. So any Cauchy sequence should have a limit. And beyond this, there is a Banach spaces, which are again vector spaces, but with a norm. Instead of a metric, we have a norm. So yeah, the proof can be found in Grudin's functional analysis. Okay, so how do we go about the proof? So we want to show that A is a linear, an open one, which means that if you take an open set, then the image should be an open set. Now let us say U is open, and we take an A of x inside A of U. I translate U by x, and by linearity, A of x will be translated by A of x. Now U minus x is going to be a neighborhood of U. So if I show that in the image I have an open neighborhood around 0, then I can translate it back and say that the image of U itself is open. Now I am allowed to do these translations because translation in a Banach space is a homeomorphism. So open sets remain open after translation. I can do the same with scaling as well. So now, so I can. So it suffices to look at open neighborhoods of 0 and show that in the image also I have open neighborhoods around 0, and that will prove the openness of A. So I take U to be the unit ball in X and V to be the unit ball in Y. Now, if I show that the image of U contains a scaled version of V, then I'm done. So I have U, which is a unit ball. Now I scale U by all the integers. That will cover all of X. So I look at U and then I look at 2, 3, and so on. Now because A is surjective, the images of these KU will cover Y. Because anything in Y is the image of some point in X, and that point will be in some KU. So I have A of KU. Now I take their closures so that I have closed sets. So I can write Y as a countable union of closed sets. Namely, countable union, the union over K of A of KU closure. Because Y is a Banach space, it's a complete metric space. So it's a Baire space by the Baire Category Theorems. So I know that at least one of these A of KU closures has non-empty integral. So suppose I pick one of them, and let's say it has there's this point C, and there's a ball of radius R around C inside A of KU closure. So what does that mean? That means that any V in V, so V is this, capital V is the open ball around 0 in Y. So now C plus RV is going to be in A of KU closure, because any point in the R ball around C is of the form C plus RV for some V in capital V. Now by the linearity of A, I have that RV is contained in A of KU closure plus A of KU closure. And that is contained in A of 2 KU closure, because that's just limits. So basically anything in the closure of KU, A of KU, is a limit of points from A of KU. and A is linear. So I can add them up, and I know that RV is going to be contained in A of 2K closure. Now, again, by applying linearity of A, I can scale everything by 1 by R. So I know that V is contained in A of LU closure, where L is 2K by R. So what does this mean? This means that if I take any V in V and any epsilon greater than 0, then there is some x in the L ball around 0, such that A of AX is within epsilon of V. Now we claim that V is actually contained in A of 2LU. And then, so if I know that V is contained in A of 2LU, then I can scale it down and I'll know that some V by 2L is contained in A of U. So how do we go about showing that V is contained in 2LU? One idea is that we could take a sequence Xn in LU and try to approximate V. But the problem is that the sequence I take, first thing is that there's no reason it should converge on the X side. Okay. Yeah, and the second thing is that because A is not assumed to be injective, even though I can take sequence A of Xn, there's no, I cannot take the pre-image uniquely. So instead, what we do is we approximate V as a sum of things from A of X, A of U. So observe that because V is contained in A of LU closure and A is linear, I can scale things down. So I know that V by N is going to be contained in A of L by N U closure. Okay. So first what we do is we obtain an x1 with norm less than L, such that AX1 is within half of V. Now this V minus AX1 is an element closer to 0 than V. So we can obtain an x2. So again, we are going to be using this V by N being in A of L by N U closure. So we find an x2 with norm less than L by 2, such that AX2 is within 1 by 4 of V minus AX1. And I repeat this process. Having obtained x1 through xn minus 1, I find an xn with norm less than L by 2 power n minus 1, such that this inequality holds. V minus A of x1 through x1 plus so on till xn is less than 1 by 2 power n. Now, because the norms of this xn converge, I know that summation of xn is defined in X. That requires the fact that X is a Banach space. So let the sum be X. The sum is defined determined uniquely. So the sum is X, and each of these partial sums are getting closer to V, and A was assumed to be continuous. So by the continuity of A, I know that AX is V. So we have again by triangle inequality, I know that norm X is less than 2L. So I find I get something in the 2L ball around 0 such that its image is V. So I get capital V is contained in A of 2LU. So A of U will contain the V by 2L ball. And this proves the theorem. So now, given any arbitrary open set around 0 in X, I scale U so that the scaled version will land inside the open set. Now I scale V appropriately so that the image will contain this scaled version of V. Then I'm done. I have a neighborhood around 0 in the image. Now for any other point, I can just translate things around, and translation and scaling are homeomorphism. So I'm done. So A is an open mapping. Now, how can I use this open mapping theorem? Well, see, we have two vector spaces basically, and a linear surjection between them. Now, if N is the kernel of A, then I know that A will induce this morphism from X mod N to Y, which is a vector space isomorphism. And I know it's continuous because I'm giving X mod N the quotient topology. So I have X to X mod N, and then I have to Y, which is an inducement. This quotient topology is given by this equivalent relation that X and Y are related if their difference is in N. Anyway, so now the induced map is going to be continuous, and it's a linear isomorphism. And it's open because the projection from X to X mod N is open, and X to Y, the map A from X to Y is also open. So the induced map from X mod N to Y is an open continuous linear bijection, which means it's a linear homeomorphism. So that's the result we get. That's a corollary of the open mapping theorem. So now an interesting thing is what happens in the finite dimensional case. So in the finite dimensional case, we don't really need the Baire category theorems. So suppose x and y are finite dimensional. So for example, Rn or Cn with the usual metrics, those are actually complete, those are actually Banach spaces itself, but we don't need that property. Now, again, when we have a linear surjection, we have this induced morphism from x mod n to y, which is going to be an isomorphism, a linear isomorphism. And because we are dealing with finite spaces, finite dimensional spaces, both the maps A bar and its inverse are given by matrices, so they are continuous. So we have this continuous map from x mod n to y, and we have this projection from x to x mod n. This projection is an open map because we can write x as a sum, a direct sum of the kernel and the other thing, the range x mod n. So we have this projection from x to x mod n, and we have this open map from A to x mod n to y. So the composition is open. Now, why does this? So this proof works well in the finite dimensional case. So where does it fail in the infinite dimensional case? Thing is that here in the finite dimensional case, we use the property that we have matrices in one. So it's easy to show continuity in the case of matrices, but in general, we don't really have it. It's a consequence of the bounded inverse theorem, which I'll come to later. But the thing is that we don't, it's not guaranteed that the inverse, even when it is defined, the inverse need not be a continuous. It's not guaranteed. So that's going to be the bounded inverse theorem. And the bounded inverse theorem, I'll be proving it as a consequence of the open mapping theorem. So there's no escape from the open mapping theorem as of before the bounded inverse theorem, I'd like to prove the closed graph theorem, which is another fundamental theorem in functional analysis. So there are two versions of the two theorems that go by the name of closed graph theorem. So if you have two spaces x and y and a map between them, then I can look at the product space x cross y with the product topology, and the graph is going to be the subset, the set of all x comma f of x such that x is in x. So now the closed graph theorem basically relates the continuity of f to the property of to the subset to the graph of f, which I call gamma f, in as a subset of x cross y. Both the theorems, both the versions say that f is continuous if and only if the graph is closed. So there's the topological version which says that if I have two topological spaces and y is a compact Hausdorff space, then the result holds. And the functional analysis version says that a linear map between two Banach spaces is continuous if and only if the graph is closed. I'll be proving the functional analysis version. If someone is interested, then I can prove the topological thing in the end. So now the proof of the functional analysis. So we prove the one way first. Suppose f is continuous. Now to show that gamma f is closed, I need to show that given a point outside it, I need to find a neighborhood around it. So I take x comma y in gamma, not in gamma f. So that means y is not f of x. Now y is a Hausdorff space. So in Banach spaces or in the compact Hausdorff space, I have y is always a Hausdorff space. So yeah. So I obtain u and v, which are disjoint neighborhoods of y and f of x. Now, by the continuity of f of x, I find an open w such that it is contained in the inverse of v. Now I just look at w cross u. So w cross u contains xy, and it's disjoint from gamma because anything in w by definition lands in v, and v is disjoint from u. So I find this neighborhood w cross u of xy, which is disjoint from gamma. So that proves that gamma is a closed subset of x cross y in the product topology. And yeah, note that this direction only requires that y is a Hausdorff space. So this direction holds in the proof doesn't change for both the versions of the theorem. Now in the other direction, assume that the graph is a closed subset. Now we have metrics on x and y, and these metrics we can use these metrics to define another metric on x cross y. So for example, you could just take the square root of sum of squares, and in this metric, the topology is nice, and we can talk of sequences and their limits. And it turns out that the sequences converge or are Cauchy if and only if the coordinates are Cauchy or convergent. And yeah, and because x and y are complete, we are dealing with Banach spaces. So x and y are complete, which will mean that x cross y is also a complete metric space. Now f is linear, so gamma f is going to be a linear subset of, it's going to be closed under addition and scaling. And we assume that gamma f is a closed subset. So that means that, so suppose we have a Cauchy sequence in gamma f. So this Cauchy sequence will have a limit in x cross y. And because gamma f is closed, that limit will land in gamma f itself. So in this way, when I restrict the metric from x cross y to gamma f, I'll know that gamma f is a complete metric space. Actually a Banach space, but complete metric is sufficient. But, yeah, so gamma f is a complete metric space. Now I have this projection from gamma f to x, projection to the first coordinate. It's quite clear that this projection is a continuous linear bijection. It's continuous because we can just argue by taking sequences. So it's a continuous linear bijection, and we can use the open mapping theorem because we have complete metric spaces on both sides. So by the open mapping theorem, this pi1 is an open map. So the pi1 inverse is continuous. Now pi1 inverse will take any x to x of x. So I compose, now I project to the second coordinate. So pi2 is the second projection. Then I'll have f as pi2 composed with pi1 inverse. So pi1 inverse will send x to x of x. Then pi2 will send it to f of x. And composition of continuous maps is continuous. So f is going to be a continuous map, which is what we needed to show. Now again, just like in the open mapping theorem, the hypothesis can be weakened to x and y being f spaces. And f spaces are almost Banach spaces. It's just that they have a metric instead of a norm. And the proof doesn't really change. We did not really require that x and y have a norm anywhere. We only needed that they have a metric and that we can take this metric to x cross y, which you can do in f spaces also. So the proof doesn't really change, and we have the same theorem for when x and y are f spaces. Okay, now we come to this bounded inverse theorem. All it says is that if you have two Banach spaces and a linear map between them, a bounded linear map, when it is invertible, the inverse is also bounded. Now I'll be needing this another lemma which says that linear map is going to be bounded if it's continuous. So assuming that lemma, this bounded inverse theorem is a direct consequence of the open mapping theorem. So T will be a continuous linear surjection, which means it's an open map. So T being open means the inverse is continuous. So the inverse is continuous, and by the lemma, the inverse is going to be bounded. So that's trivial once we have the open mapping theorem. And this lemma is also quite easy. So we want to show that T is bounded, meaning norm of Tx is less than some constant times norm x, if and only if it's continuous. So so to show continuity, it suffices to look at the sequential definition of continuity because we have metric spaces. And by linearity, it suffices to look at the continuity at 0. Now, if it is continuous at 0, then there's a delta such that whenever norm x is less than delta, norm of Tx is less than 1. Now, by using linearity, we can show that norm of Tx is less than 1 by delta norm x. And in the other direction, if T is bounded, then norm Tx is less than some constant times norm x. And so now, if norm x is very small, then norm Tx is going to be very small. So we have continuity at 0, and by linearity, we have continuity everywhere. So that was the bounded inverse theorem. Now there's this one last theorem I'd like to share. This is the uniform boundedness principle. So now again, the proof is similar to the open mapping theorem. We take something which we know has non-empty interior and write it as a union of closed sets. So if we have x a Banach space and y a non-linear space, and if we have a family of continuous linear transformations from x to y, such that whenever I fix a point x in x, I get this sequence Tnx. So if this sequence Tnx is a bounded sequence for every x in x, then one can show that the whole the norms of Tn is uniformly bounded. So how do you prove this? Well, we look at xk to be the set of all x, so that the norm of Tnx is bounded by k over all n. Norm supremum over n of t norm Tnx is bounded by k. Then each xk is a closed set because the moment some tmx has norm greater than k, I can find a ball around there and then use the fact that tm and norm is a continuous function. So xk is a closed set, and and by assumption, I know that everything is covered in it. So I can write x as a union of xk. That's by assumption. So x is a Banach space, so it's a Baire space. And by Baire category theorem, I know that some xn will have non-empty integral. Now, so take that xn and this xn. So that means that there's some x0 and epsilon greater than 0, such that the ball of epsilon ball around x0 is contained in xn. Because xn is a closed set, I can take the closure of the ball and still remain in xn. Now, given if I have any u with norm less than 1 and I follow this chain of inequalities, so t of u is less than t of u is equal to t of x naught plus epsilon u minus t of x naught with an epsilon u inverse pulled outside, and then I apply the triangle inequality, and because x0 plus epsilon u and x0 are both in xn, I have the norms bounded by n, so I get that norm of tu is less than epsilon inverse 2n times 2n. So there's this constant which is independent of which t in the family we take. So every t is bounded by the same constant, has norm bounded by the same constant, and that proves the uniform boundedness principle. Okay, so that's really the end of my talk. There's just a few more things I would like to say. So, like I said, this Baire category theorem is a very useful result, and since most of the time we are dealing with Baire spaces, we can apply them all the time. Apply this the Baire condition all the time. So here's this one more result that's of interest to analysts. So if X is a space and Y is any metric space, and we have the sequence of continuous functions which converge pointwise to some f. So it is of interest to know when where f is continuous, or so on. So the thing is that when X is a Baire space, one can show that the f is continuous almost everywhere, meaning that the set of continuity points is dense in X. And that's quite a useful result. Basically, it says that the pointwise limit of continuous functions when Y is a metric space and X is a Baire space is almost everywhere continuous. And yeah, that's the last theorem I would like to mention. And one more thing is that so while proving the Baire category theorems, there was this repeated use of the choice function. Now I didn't state it explicitly, but every time we picked xn or picked the un and so on, there was this use of axiom of choice. Okay, so now this axiom of choice is a tricky question in mathematics, and one would like to know when exactly one is using the axiom of choice and when one is not, or rather, one would like to know what results require which axioms. So it turns out that the first theorem, meaning that the complete pseudometric space is a Baire space, so that theorem is equivalent to the axiom of dependent choice over the Zermelo-Frankel axioms of set theory. However, we can weaken the condition to make it prove it without choice. So if we assume that the complete metric space is also separable, meaning it has a countable dense set, then one can prove that the space is a Baire space without using choice over the Zermelo-Frankel axioms. So one way to think about it is that once you are given a countable dense set, you are basically given a choice function. You can a countable choice function. So I mean, I don't know the proof, but that's one way to think about it. I have linked the paper in the end. And the other theorem. So what did we do? We proved the Baire category theorems, and to prove that Banach spaces are Baire spaces. And then we proved the Open Mapping Theorem, and we used the Open Mapping Theorem to prove these other two theorems, Closed Graph Theorem and the Bounded Inverse Theorem. But we required to prove the Open Mapping Theorem first. But it turns out that under some reasonable assumptions, these three theorems are equivalent to each other. And that's why they are quite fundamental in functional analysis. And I have linked the papers in the end for those also. And that concludes the talk. If someone is interested, I could explain the two things, the topological version of closed graph theorem and the result about locally compact spaces. Thank you for this.
Thank you, Shrivathsa, for the talk. We have a 10-minute time period for any questions, if anyone has any.
So I don't think anyone has any questions. Thank you very much for the talk. I
Thank you for
hope
this opportunity.
everyone enjoyed it. So join us next week for a talk on the introduction and history of prime number theorem and an elementary proof for the same by Tarushri. So thank you very much.
Thanks.